In the grand story of the cosmos, there are certain bedrock facts, numbers so fundamental to our understanding of reality that to challenge them is to challenge everything. The most important of these is the age of the universe itself. According to our best science, the product of a century of observation and calculation, the universe began in the Big Bang 13.8 billion years ago. This is our ultimate cosmic horizon, the absolute beginning of time, space, and matter as we know it. Nothing can be older than the universe, for the simple reason that before it, there was no before. So imagine you're an astronomer. You spend your life looking at the light from ancient stars, decoding the secrets of the cosmos. One day, you point your telescope at a seemingly unremarkable star, a faint point of light in our own galactic backyard. You run the numbers, you check your models, and you calculate its age. The answer that comes back is 14.5 billion years. It's a number that cannot be real. It's a result that breaks the most fundamental rule of existence. You've just found a star that appears to be older than the universe itself. This isn't just a small statistical error or a minor curiosity. It's a profound, logic-defying paradox. It's like an archaeologist finding a Roman coin dated to 500 BC, or a historian finding a photograph of Napoleon checking his smartphone. It's an object that, according to the timeline of reality, simply should not exist. This is the story of that star, an object officially known as HD 120283, but more famously nicknamed the Methuselah Star. It's the story of a cosmic contradiction that sent shockwaves through the astronomical community and forced scientists to re-examine the very foundations of how we measure time on a cosmic scale. This is a scientific detective story, a hunt to solve an impossible crime against the laws of time itself, measuring the immeasurable before we can appreciate the absurdity of a 14.5 billion-year-old star. We first have to understand why scientists are so incredibly confident that the universe is only 13.8 billion years old. This number isn't a guess. It's the result of multiple independent lines of evidence that all point to the same precise conclusion. It is the cornerstone of modern cosmology. The Great Expansion. The first clue came in the 1920s from the work of the American astronomer Edwin Hubble. Working from the Mount Wilson Observatory in California, Hubble made a discovery that completely changed our perception of the universe. At the time, it was widely believed that our Milky Way galaxy was the entire universe. But Hubble, observing faint fuzzy patches of light then called spiral nebulae, was able to measure their distances. He proved that these objects were not inside our galaxy. They were other colossal galaxies, or island universes, millions of light years away. This discovery expanded the known universe by an almost infinite amount, but it was his next discovery that laid the foundation for modern cosmology. Hubble began to analyze the light from these distant galaxies, and he noticed something peculiar. The light was redshifted. This is a phenomenon based on the Doppler effect, the same principle that makes an ambulance siren sound higher-pitched as it comes towards you and lower-pitched as it moves away. With light, an object moving away from us will have its light waves stretched out, shifting them towards the red end of the spectrum. An object moving towards us would be blue-shifted. Hubble found that virtually every galaxy he looked at was red-shifted. They were all moving away from us. But the truly revolutionary part was when he compared a galaxy's redshift to its distance. He found a clear, linear relationship. The farther away a galaxy is, the faster it is moving away from us. This became known as Hubble's law. The implication was staggering. The universe wasn't a static, unchanging void. It was expanding. The very fabric of space-time was stretching, carrying all the galaxies along with it. This discovery provided the first real method for calculating the age of the universe. If everything is flying apart, it means that in the past, everything must have been closer together. Imagine watching a video of a fireworks explosion. By measuring the speed at which the sparks are flying apart, you can rewind the video in your mind and calculate the exact time and place of the initial explosion. The expansion of the universe works the same way. The rate of this expansion is known as the Hubble constant. By measuring this constant with increasing precision, astronomers could run the clock backwards to a single point in time when the entire observable universe was compressed into a hot, dense state of unimaginable energy. That point in time was the Big Bang. Early calculations were rough, but they all pointed to an age of many billions of years. The echo of creation. The second, and even more precise line of evidence came from an accidental discovery in 1965. Two radio astronomers, Arno Penzias and Robert Wilson, were trying to use a large horn antenna for radio astronomy, but were frustrated by a persistent, faint hiss of background noise that seemed to come from every direction in the sky. After exhausting every possible explanation, including famously cleaning out pigeon droppings from the antenna, they realized the noise was not from Earth. It was cosmic in origin. They had stumbled upon the cosmic microwave background, CMB, the single most important piece of observational evidence for the Big Bang. This faint glow of microwave radiation is the afterglow of creation itself. It is the residual heat from the Big Bang, a baby picture of the universe from when it was only about 380,000 years old. At that moment, the universe had cooled enough for the first stable atoms to form, which allowed light to travel freely through space for the first time. For the past 13.8 billion years, that ancient light has been traveling across the cosmos, its wavelength stretched by the expansion of the universe from a brilliant hot glow into the cold, faint microwave radiation we detect today. This CMB is not just a uniform hiss. It contains incredibly tiny temperature fluctuations, differences of only a few millionths of a degree. These fluctuations represent the seeds of all future structure in the universe, the slight variations in density that would eventually grow under the influence of gravity into the galaxies and galaxy clusters we see today. By studying the precise pattern of these fluctuations with a series of incredibly sensitive space telescopes, COBE, WMAP, and most recently the Planck satellite, cosmologists have been able to create what is known as the Standard Model of Cosmology, or Lambda CDM. This model can predict the composition, geometry, and age of the universe with astonishing accuracy. And the age it predicts, based on the most precise measurements of this ancient light ever made, is 13.8 billion years, with an uncertainty of only about 20 million years. This is the cosmic speed limit, the age of the house itself. No guest could have possibly arrived earlier. Reading a star's birth certificate. So, with one half of the paradox established with incredible certainty, the investigation had to turn to the other half. The star. How do astronomers determine the age of a single star with enough precision to challenge the age of the entire universe? It's a process of stellar forensics, piecing together clues written in the star's light to reconstruct its long and detailed history. Clue number 1. The star's DNA, metallicity. The first and most important clue to a star's age is its composition. In the moments after the Big Bang, the universe was an incredibly simple place, composed almost entirely of the two lightest elements, hydrogen, about 75%, and helium, about 25%, with a tiny trace of lithium. Every other element on the periodic table, the carbon in our bodies, the oxygen we breathe, the iron in our blood, the gold in our jewelry, did not yet exist. These heavier elements, which in astronomical jargon are all collectively known as metals, were forged later, in the intense heat and pressure of stellar cores and the cataclysmic explosions of supernovae. This simple fact allows astronomers to categorize stars into generations or populations. The theoretical first-ever stars, born from the pristine gas of the Big Bang, would have had 0 metals. These are called population 3 stars. They would have been incredibly massive and short-lived, and we have not yet directly observed one. The next generation, born from the ashes of those first stars, are called population 2 stars. They are ancient and extremely metal-poor, containing only a tiny fraction of heavy elements. Much later generations, including our own Sun, are population 1 stars. They formed from gas clouds that had been enriched by many cycles of star birth and death, and they are therefore relatively metal-rich. Astronomers can determine a star's metallicity with a technique called spectroscopy. By passing a star's light through a prism-like instrument, they can spread it out into a rainbow or spectrum. This spectrum is not perfectly smooth. It is crossed by thousands of dark, thin lines called absorption lines. Each line is a chemical fingerprint corresponding to a specific element in the star's atmosphere that is absorbing light at that exact wavelength. By analyzing this unique chemical barcode, scientists can determine a star's composition with incredible precision. A star with very few and very weak metal lines is undeniably ancient. Clue number 2, the star's life cycle, evolution and brightness. The second clue to a star's age comes from understanding its life cycle. The life of a star is a constant battle with gravity, and this battle is governed by the star's mass. In the 20th century, astronomers developed a powerful tool for understanding this life cycle called the Hertzsprung-Russell (HR) diagram. This diagram is essentially a family portrait of the stars, a graph that plots a star's true brightness, its luminosity, against its surface temperature. When you plot stars on this diagram, they don't appear randomly. They fall into distinct groups. The most prominent of these is a long diagonal band called the main sequence. This is where stars spend about 90% of their lives, in a stable phase, where they are happily fusing hydrogen into helium in their cores. A star's position on the main sequence is determined almost entirely by its mass. Massive stars are very hot and very luminous, appearing in the upper left of the diagram. Less massive stars, like our Sun, are cooler and dimmer, appearing in the middle. The least massive stars, red dwarfs, are very cool and very faint, appearing in the lower right. A star's mass also determines its lifespan. Massive stars have more fuel, but their immense gravity causes them to burn through it at a furious rate. They live fast and die young, exploding as supernovae after only a few million years. Less massive stars, however, are cosmic misers. They sip their fuel slowly and can live for billions or even trillions of years. This is the key to dating a star like the one in our story. A star's age can be determined by tracking where it is in its life story. HD 140283 is a relatively low-mass star, so it has a very long life. It has already exhausted all the hydrogen fuel in its core, meaning it has finished its time on the main sequence. It has now entered the next phase of its life, beginning to swell into a subgiant as it prepares to become a red giant. For a star at this specific stage of its evolution, its luminosity, its true intrinsic brightness, is a very sensitive indicator of its age. The brighter it is, the more evolved it is, and therefore the older it is. So to get the age, you need two things. You need to know from its metallicity that it's an ancient population 2 star, and you need to get a hyper-accurate measurement of its luminosity. The Methuselah Star now. Let's turn our attention to the star at the center of this cosmic crime scene, HD 140283, the Methuselah Star. It's located just under 200 light-years from Earth, which in galactic terms makes it our next-door neighbor. It's so close and bright it can be seen with a good pair of binoculars, and it has been known to science for over a century. For a long time it was just another entry in a catalogue, but as astronomers began to study it more closely, they realized it was something special. First, they noticed its incredible speed. It is blazing through our local galactic neighborhood at about 800,000 miles per hour. This high velocity is a telltale sign that it's not a native of our part of the galaxy. It's a visitor from the ancient spherical halo of stars that surrounds the main disk of the Milky Way, a region known to be populated by the galaxy's oldest stellar residents. Then came the spectroscopic analysis. When astronomers looked at its chemical barcode, they were stunned. Its metallicity was incredibly low. It has only about 1/250th of the iron content of our Sun. This was the smoking gun. This confirmed, beyond any doubt, that HD 140283 was a population 2 star, a living relic from the dawn of cosmic time, born from the nearly pristine gas of the early universe. It was one of the oldest stars ever discovered. The real investigation began in the 2000s, using the unparalleled power of the Hubble Space Telescope. An astronomical team led by Howard Bond set out to pin down the star's age with the highest precision ever attempted. They used Hubble's fine guidance sensors to make incredibly precise measurements of the star's position, which would allow them to calculate its distance through parallax. They used other instruments to get an exact measure of its apparent brightness. Once they had the distance, they could calculate its true intrinsic luminosity. They then took this luminosity value, along with its precisely measured metallicity, and plugged the numbers into the most sophisticated and up-to-date computer models of stellar evolution. These models represent our best understanding of the physics that governs how stars live and die. And then the impossible answer came back. The team's best estimate for the star's age was 14.5 billion years. The uncertainty on this measurement was about 800 million years. This meant its age could be as low as 13.7 billion years or as high as 15.3 billion years. This was the moment the paradox was born. The precisely known age of the universe, 13.8 billion years, fell right in the middle of this range. But the best fit age for the star was significantly older than the universe itself. Even at the absolute lowest end of its uncertainty, its age was uncomfortably close to the age of the cosmos, leaving almost no time for the first stars to form after the Big Bang. It was a scientific crisis. The star was a guest who had seemingly arrived at a party before the house was even built. The Methuselah Star wasn't just old, it appeared to be impossible, solving the cosmic crime. In science, a paradox like this is a wonderful gift. It's a flashing red light that tells you something is wrong. But scientists didn't throw out the theory of the Big Bang. The evidence for the universe's age was overwhelming. They knew with near certainty that the error had to lie in the calculation of the star's age. The measurement of 14.5 billion years was the best they could do at the time, but it relied on several assumptions and measurements that all had their own small margins of error, their own error bars. The solution to the paradox had to be hiding within those uncertainties. The investigation turned to re-examining every piece of evidence. Uncertainty. Year 1. The tyranny of distance. The single most critical factor in determining a star's luminosity, and therefore its age, is its distance. An error in the distance measurement creates a huge error in the final age calculation. The primary method for measuring the distance to nearby stars is called stellar parallax. Image explaining stellar parallax. The principle is simple. Hold your thumb out at arm's length and close one eye, then the other. Your thumb will appear to jump back and forth against the distant background. This apparent shift is parallax. Astronomers do the same thing using the Earth's orbit. They measure a star's position against distant background galaxies and then measure it again 6 months later when the Earth is on the opposite side of its orbit. The tiny angular shift they measure allows them to calculate the distance to the star using simple trigonometry. The initial Hubble measurements of HD 140283's parallax were the most precise ever made at the time, but they still had a small but significant margin of error. Their slight overestimation of the star's distance would make it seem intrinsically brighter than it really was, which in turn would lead to an overestimation of its age. The case needed a better witness. That witness arrived with the launch of the European Space Agency's Gaia Space Observatory. Gaia's sole mission is to create a hyper-accurate 3D map of over 1 billion stars in our galaxy, measuring their positions, distances, and motions with a precision thousands of times better than anything before. When Gaia turned its eye to the Methuselah Star, it provided a new, refined parallax measurement. This new data suggested the star was slightly farther away than the original Hubble measurement, which adjusted its luminosity and, by extension, its age. This was the first major step in resolving the paradox. Uncertainty, Runpa 2, the recipe for a star. The second area of uncertainty was in the computer models of stellar evolution themselves. These models are incredibly complex, but they are only as good as the physics we put into them. The models for ancient, extremely metal-poor stars were still being refined. One crucial detail was the star's specific chemical mix. While the star was extremely poor in iron, subsequent studies found that it had a higher than expected ratio of oxygen to iron. Oxygen is a key element in the CNO cycle, a process of nuclear fusion that becomes important in stars slightly more massive than the Sun. The precise amount of oxygen in a star's core affects the rate at which it consumes its fuel and evolves. The original models had to make assumptions about this ratio. By updating the models to include the newly measured higher oxygen abundance, Scientists found it had a subtle but important effect on the star's life cycle, nudging its calculated age downwards once again. Uncertainty. But 3. A star's inner life. A third, even more subtle physical process also needed to be considered: helium diffusion. Over the course of 13 billion years, the heavier helium atoms produced by fusion in a star's outer layers will slowly sink towards the core due to gravity. This gradual settling process changes the chemical composition of the different layers of the star, which in turn affects the rate of nuclear fusion. The earliest models hadn't fully accounted for this slow, methodical process. When this effect was properly included in the simulations, it provided another small but significant correction, again reducing the star's estimated age. With all these refinements in place, a better distance from Gaia, and more sophisticated stellar models that included the star's specific oxygen content and the effects of helium diffusion, the team of astronomers re-ran the calculations one final time. The new revised age for the Methuselah Star came back at approximately 12 billion years. The uncertainty on this new measurement is still significant, about 500 million years, meaning its true age could be anywhere from 11.5 to 12.5 billion years. The Methuselah Star was not older than the universe. It was just one of the oldest things in it. It's a living relic from the cosmic dawn, a time capsule that was likely born when the universe was less than 2 billion years old. It has been shining for nearly the entire history of time. The quest to understand its impossible age didn't break our understanding of cosmology. Instead, it drove us to refine our understanding of stars. It forced us to get better measurements and build more accurate models. The story of the Methuselah Star is a perfect illustration of how science works at its best. It's not about being right all the time, it's about chasing down anomalies, embracing paradoxes, and relentlessly refining our knowledge until an impossible object becomes a beautiful and profound truth.